What is this beam pattern?
So that is like a right.
So let's recognize some of the components inside first.
Okay. So I see a delta function.
This one is a delta, right?
Mm-hmm.
What's this?
That's like a direct comp of different amplitudes,
So it's like a
like an inverse triangle.
And
Oh, yeah,
the littlest one is at -4. Going to 5?
No, you're right. Sorry, yeah, you're right. You're right. No, you're right. You were right the first time.
I was right?
Yes.
Oh yeah. But the other way we can do that too. It's just a rectangle minus
Yeah.
Mhm.
a path. And then there's that bunch of deltas.
No.
No.
No. It's actually already. It's
Right.
like,
So this part is like this across that.
okay.
Oh.
Yeah, you're using the same
Yes.
thing you used up there.
Yes, that is, yes.
So it's 3 components. Then we do convolution. Delta becomes phase shift, right? This becomes the sink square.
Mhm.
Then many of them. Like discrete version becomes many of the sink square. So it's like a bunch of sinks.
Yep.
Yep. Are there other ways to do this?
I think that's like a pretty straightforward way to go about it.
Right. I mean, if we do not recognize this, we can do this as many of the flat one. Then it adds up. And, if we recognize it, it's pretty straightforward. So this is the first part where we can find the oh, quick question. What would be the beam width? Like without doing all the calculations, we know that the beam width of that is still lambda over L, right?
Mm-hmm.
Why is it lambda for a rectangular? It's lambda
Right.
over L.
For since it's convolved, triangle is convolved of 2 rectangles. Right.
Yeah.
Yeah, but it should still be lambda
Oh, yeah.
over L.
Right.
Yeah, because it's just sink squared, right?
Yeah.
You're not changing any of the zeros, are you?
No, you're not changing any zeros. I agree. Over 2.
Yes.
Oh yeah. So this kind of array will give you a beam width that's lambda over L.
Yes.
Here we know if you convolve it, and like if you convolve this, it's still lambda over L.
Mm-hmm.
If you convolve it, it becomes
Mhm.
like regardless of magnitude, this becomes L over
Lambda.
minus, and this L over lambda. So we can count here. The width of this is
5.
5, yeah, 5 to 5. All right.
Why is it not -4 to 4?
Because
No,
maybe 4 is 1 already.
Yeah.
Right. And if we plug in 4, it's 1.
Uh-huh.
So it's actually
5.
0 and
Oh,
5.
I mean 0.
Yeah.
Yes.
So we know this is 5. The beam width is 1 over 5.
Oh, that's cool.
So like it's comparison technique that you knew for general let's say what that is. Here you know the value is 5, you plug in, you get.
Kind of like you backtracking.
Mm.
Okay. Yeah, then it's the exercise of doing the steering that to make sure there's no main lobe here. Oh, quick question. What's this?
Isn't that standard law what we did before?
I don't really think about it. Okay.
What is it? What's the distance between? What's the delta S between two gradient lobes?
Okay. So
So right
my
there.
delta L is that. Wait, no, that's delta U, right?
No.
Distance here. So
What's delta U?
1.
Okay.
So if
Delta
delta
S is
1 over
delta U,
so 1 over
delta S is 1. Okay.
So how did you get that the delta U is 1?
Oh, look at this. First, we know on this example we give
Yeah,
here,
but-
delta U is like the distance between these two things.
That doesn't
Right.
really give you delta U be 1.
Oh, yeah, right.
It's
It's
still
just
1 over
delta
delta U.
Yeah.
You can say that delta U is 1 from there, because that's amplitude. I agree with that.
Right.
But
Okay.
nothing in that expression tells you what delta U is.
Right. Yeah. Sorry. So we don't know delta U yet.
Okay, were we given delta U? Because I got the not picture, the cone picture.
Oh yeah, we were given delta U is like 0.5.
Oh,
Okay.
okay. Then I would guess that.
Okay.
So S would be 2.
So this is actually -5 delta U. It's not -5 exactly.
Mhm.
Right. So then we know that the beamwidth becomes 1 over that
Because there's a lambda kind of like in
Yeah.
there, so.
1 over 5 delta U.
You need to have some sort of like delta U factor, otherwise you have just
Yeah.
like a sphere number, which does not make sense.
Cool. So these are all the higher level like examples I want to give. That some of the techniques is summarize that in discrete version arrays. We need to be able to recognize components. Well, in continuous array as well to recognize components and then find the beam pattern of each components. Then either convolve or multiply them. And then some useful things to know is the beam width, how to calculate that, and like range in terms of how far you can steer before you get gradient lobes in your real space. Okay. I highly recommend we try out many different examples of convolution. For say like for me, I didn't know convolution until I took that class, so it does take me a while to learn it. And
You
then,
went through it again in 6431.
yeah, then I'm like, yeah, I know convolution now. So convolution is definitely, and then there's the table of all useful convolution. That if we don't have a copy, I can scan this one and send to everyone. Then that shall conclude our study today.
Wow, you ended exactly at 8.
Cool.
So professional.